your 203 course, you would have talked about a collection of special types of distributions, right? Each of them having their own set of parameters, right? So those parameters for those distributions describe what that PDF looked like. Right? So often what we think about these are as population parameters, right? So really it relies on the entire population. And if we know the entire population, we would know exactly what that distribution looks like, and we can find those parameters precisely. Right? So some things that we often look at are things like the mean, mu, or the proportions, p, or the variance, sigma. Right? So we'll be kind of looking at these in the context of a handful of these distribution functions today. Now, like our discussions previously, we can't directly observe or find these values, right? Because that would rely us having the information about our entire population, which we've talked about before is not really a tenable option. Right? So rather than trying to find these values precisely, they're often kind of treated as these unknown values that we're interested in learning more about. Right? So really those parameters are just numbers that describe a population. So since we can't observe those directly, right, often what we do is we try to take a sample from that population we're interested in, and we try to find estimates of those parameters that we're interested in. Right? So for instance, we've looked at things like the sample mean and the sample proportion and the sample variance last class. Right? But rather than just kind of using these plug-in estimators, right, we really want to get a sense of where they came from. Right? So our objective today is going to be trying to develop some methods for finding those types of equations, right, based on this idea that we have a sample from our data, our population of interest. Right, so it's shifting gears a little bit because our sample data last class, we were talking about it as being a random variable, right? And we want to kind of understand the variation and where it's centered. Right? It's shifting gears a little bit in the sense that in this lecture, we assume that we've taken that sample, right? And we'll be talking about the likelihood in particular where that sample is already set, so it's no longer a random variable. Right? So I'll try to emphasize that as we go along. Okay, so our schematic here is that we have this population that we're interested in, and we take a sample from that population. Right, so most of this course is going to be focused on doing those kind of statistical analyses, but it's really important to still understand that the sampling of that population is a pretty important thing to think about. Right, so we want this sample to be representative of the population. Right, so we talked about things like biases before. We just sampled a basketball team. We were trying to estimate heights, for example. Right, so remember, under that hood, we want to make sure that we're doing a simple random sample. Right, so this is just kind of one example of the sampling technique. Right, but for the sake of this course, we'll usually be assuming that we're taking a simple random sample. Right, so just a reminder that this means that every element of the population has an equal probability of being selected. Right, so you can think I take all those people, I put them in a bag, shuffle them up, right, and then I take one out at a time. Right, so they all have an equal probability of being sampled. Right, and why is this important? Right, because it eliminates biases. Right, so remember at the end of the day, we want to take a sample to do inference on that population. Right, and that inference is not going to be sound if our sample is biased. Right, so this allows us to do our statistical inferences that we're leading up to and make our results generalizable to the public, right, so to that population that we're sampling from. Okay, so supposing we're beginning with a simple random sample of size m from the population, we are interested in these parameters, right? So these, again, are assumed to be unknown to us, right? But we know what they are, right? Because we're going to assume our population follows some specific distribution, right? We know a little bit about these specific distributions right, from our discussions in Stat 203. Now, we're going to be focusing today on how do we get those estimators that find the best possible estimates of those population parameters. Right, so to add some context, right, maybe we're assuming these populations follow a normal distribution. Right, so our normal distribution, right, you'll see me using this notation, right, so we have this PDF, right, so this is a function of our x, and then I'm using a semicolon. Sometimes people use a pipe here, right, but given these parameters mu and sigma, right, because our PDF for the normal distribution has two parameters, right, and this basically dictates how this distribution looks like. It'll tell me where that bell shape is centered, and it'll tell me how fat that bell shape is. Right, and I change those I change those parameters of that distribution. I change the shape of that bell curve. Right, so we go in saying we assume that it follows a normal distribution. I know that it's this bell shape, right, but I want to determine where's a likely place that it's centered and what's a likely shape in terms of the standard deviation. Right, so in order to do that, what we do is we take a simple random sample from that population. Right, and then I basically want to use that random sample, right, to give me some sort of plug-in estimate to give me a guess for these two parameters, right, that we don't know. Right, of course, our population of interest doesn't have to assume to be normal, right? I can have said, okay, well, I'm observing a different phenomenon, right, and maybe this has some exponential distribution, right? So again, using that same notation, right, this is still a function of f given some parameters, right? The only parameter in the exponential distribution is this lambda parameter, right? So this rate parameter, right? And this is our PDF, right? And this is, unlike the normal distribution that's defined for all real values, this is only defined for positive non-negative values. Right, so in the same vein, I want to say, okay, well, I know that it has this shape, right? And this lambda is going to dictate the shape of that exponential curve, right? So I want to take a simple random sample to allow me to estimate that thing as best as possible, right? So we're doing a data-driven kind of guess at what this population distribution actually looks like. Right, another example we can look at is the beta distribution, right? This is a popular distribution because it's defined on 0 to 1, which helps model things like proportions. Right, so we have this beta distribution, which has two parameters, alpha and beta, often referred to as shape 1 and shape 2, right? And it's defined on 0 to 1, right? And it has this PDF, where this b is the beta function. Right, and again, we take a sample and we want to find some plug-in estimates for alpha and beta. Right, and again, this alpha and beta is going to change the shape of this beta distribution, right? So this beta distribution is quite flexible. Now, just to add some more generalization to this kind of scheme, right, more generally, we're going to say we have some population distribution, right? This f of x that relies on these parameters, right? So I'm just going to generically call them theta 1 to theta l. Right, so we saw some examples that have just one parameter. We saw one that has two parameters. Right, so our population parameters are basically going to be these Greek letters, right? And we basically want to find a good way of estimating those population parameters. Okay, so going forward, it's important to realize that there's kind of two ways that we can answer this question about our estimates here. Right, so today we're going to be focusing on something called a point estimate. This is basically going to be a guess that's a single estimate. Right, so I'm going to provide a guess that theta 1 is equal to 8.3. Right, so this single best guess, right, will give us a sense of where we think that population parameter is. It doesn't give us any idea of our uncertainty about that. It gives us no kind of plus minus. So in a future lecture, we're going to take this a step forward by not only just giving a point estimate, but giving a plus minus about that point estimate. Right? So depending on how we sample things, what our distribution looks like, right, we might have a bigger plus minus about that, right, indicating a bigger uncertainty, right, or it might be more precise, right, we might have less plus or minus around that. And so this is going to be building up to what we'll know as a confidence interval, right? And it's going to provide a range of guesses, right? So rather than saying, I guess that theta is 8.3, right, I might say, I guess that theta is somewhere between 6.3 and 10.3, say. Okay. So just to put our sampling assumptions a little bit more detailed here. So we're going to assume that we take a sample of size n. So I'm going to just create a vector of n random variables x1 through xn. Right? And these are all independently, identically random variables from our population. Right? So this is sometimes referred to as being IID. Right? So all that's basically saying is that each of these x's follow the same distribution, right? Namely, the whatever distribution our population is. Right now, that population of interest we say has some probability distribution function if it's continuous, or some probability mass function if it's discrete, right? Which has this generic kind of formula, right? So f of x given its parameters. Right, and then theta 1 through theta L are just our unknown population parameters, which we're trying to obtain guesses for. So sometimes what you'll hear me referring to our sample as is a random independent sample. Right? So this basically just combines the idea that we are taking a simple random sample from these IIDs, right? So we have to shuffle all of our people in a bag and pull them out randomly. And in addition to that, we need to make sure that all of these people in our bag are independent from one another. Right? So we talked about violations of that previously. So if we had twins, for example, in our study, that would violate that independence assumption. Right? So sometimes I summarize this as we're doing a random independent sample, or I'll abbreviate that by our RIS sample. Now, usually if you hear in a textbook their IID, right, we're for the sake of this course, we also assume that those IIDs are a simple random sample, right? So we can basically assume that this sampling setup is being used for these problems. Okay. So we have our population parameters being our characteristics of interest, and we need to find a plug-in function to estimate those based on our sample. Right, so we're going to introduce a little bit more rigorous notation here. Right, so here I've indicated this theta. Right, so this is basically capital theta. Right, so this is trying to keep in line with what we were talking about before. Right, so we had this capital letter being a random variable. Right, so and then once it's observed, this is the observed value. Right. Now here I'm using, this is capital theta, right? So these are basically capital letters. Right? And then this thing here is a random variable, and once it's observed, right, we plug in our x's to this, right? This is going to be our observed guess. Right? So sometimes we'll refer to this as a point estimate. Right? But the same kind of parallels here. Right? We have a random variable, and once we actually take our sample, it's no longer random, right? It's the one that we have, it's the observed, and we go to the lowercase, right? So uppercase theta, lowercase theta. Right, so this capital theta is our random variable, and it's going to depend on our sample, right? So sometimes I'll be explicit and say this is basically a function of our sample, right? But more generically, I might just write it as capital theta, right, to indicate that this is our estimator. Right, so another way that we refer to once it's observed is our point estimate. Sometimes I'll just refer to it as an estimate. Right, so in terms of our notation, the estimator is our random variable, and the estimate is our observed. Right? So our point estimate, you can see here, our notation is really explicit about this, right? So these x's are no longer random variables, right? We took the sample, they're observed, we're going to put them into our equations, and we're going to get a point estimate for that value of theta. Right, so just for completion here, maybe we'll write that down too. So our actual theta, right, this is the population parameter of interest, right? some unknown value that we're trying to estimate well. Okay. I'll pause to see if there are any questions with that notation before we continue, because I'll be using those terms throughout the lecture. All right, so just to give some context to those ideas, right, if we return back to our normal population example, right, so our theta 1 in this case is mu, and our theta 2 is sigma, right? Those are our two population parameters of interest, right? So I can create a plug-in estimate. So this mu hat, right, this is basically my theta hat, right? This is going to be my plug-in estimator function, right? So I should be more specific that the thing on the right, is my estimator, right? And once I plug it in, so I take a RIS sample from the population, right? These random variables now get changed to their actual observed value, right? So I take a sample of 6 people, right? I record their height if we're talking about height, and then I take their average, right? So this value of 167.7 centimeters, this is my estimate for the population parameter mu, right? And this equation is my estimator for that population parameter mu. Now, we'll be referring to these in these theorems more generally using theta. So just to do that same example using the general theta terms, right? So we have a population distribution with unknown parameters theta 1 to theta L. We're going to have some estimator, right, which is just going to be a function of my sample, right? Where, again, this is a random variable. I'm then going to take my sample, right, and then I'm going to record their values, their x values, and then I'm going to plug it into that estimator, right? And what I get back is going to be my point estimate. And so that's our general workflow of how we operate. Okay. Now, one question that I want to pose, right, we've dealt with this results quite a bit throughout our few lectures already, but whenever we're estimating our mean of, say, a normal distribution or a population in general, right, we often just use the sample mean for estimating that, right? But my question is, why are we using the sample mean, right? We know we have other estimates of central tendency, right? So other estimates that we could have used to estimate this population parameter, right? I could have used the sample median, right? I could have used the mode of the interval distribution. I could have just selected a height at random, right, from my sample and said, I'm going to use this as my guess for mu. Right? So there's a bunch of different estimates we could achieve from a sample, right? So what makes the sample mean so special? Right? Why is it the one that we use? Why is it a reasonable guess for our mu? Right, so to answer that question, we really need some guidelines of how we should define estimators. Right? So how do we judge the quality of an estimator? Right, so we need some criteria to help us do this. Now, when I first opened this lecture, right, we were talking about finding a good guess for our population parameters. Right, but we'll kind of delve into the question of, is there a best estimator, right? Is there some criteria that we can describe that will restrict that search such that we can obtain kind of a gold standard guess? Right, so this is all kind of questions that we're going to be starting to think about and working towards over the next few lectures. Okay, so next up, right? So here we have just an open-ended question, and I just want you to kind of think about that question. Right? So what type of things would you want your estimator to have to be classified as a good guess for your mu? Right? So I'll invite you to join it either clicking this link here, or you can scan the QR code here. And so I'll give you guys a couple of minutes just to put in some ideas of what you think would make a good estimator for mu. All right, so let's look at some of the ideas that we have here. So a large RIS size, and so that's a good quality that we would want to have, because we know, or we have a general intuition, we haven't really proved this per se, right? But we know that the more samples we have, kind of the more accuracy we can have in our estimator, right? So that's something we saw in the central limit theorem, that the variance of X bar got smaller and smaller as the sample size increased. Right. Another thing that we have here is unbiasedness, right? That's a good one, right? Because we want, on average, our guess to be correct, right? So